All right, so here we are, number 7. This is section 7.1. We might finish it. We'll see. Confidence intervals. So we were doing confidence intervals. I'm sure you haven't been thinking much about them at all. Your focus has been on the exam. So let me remind you what they are. Basically, they did some kind of experiment, and they were maybe crossbreeding peas or whatever. Anyway, they got 446 green peas, 157 yellow, and they're thinking, hey, what's the true percentage of yellow peas? So first off, can we even figure what percent of those peas came out yellow? Could we add it together? Can we figure that out? Yeah, got to add it together, huh? Exactly. So if you had 446 and 157, I don't know what that is. 603. Is that what it is? Man, you're quick, Val. 603? That's 603 total peas. So how do we figure out the percentage that's yellow? So the percent yellow, percent yellow would be the 157 over the 603. 157 divided by 603. Yeah, 20, yeah. So I'm getting 0.2604, whatever. I don't know how far they want us to round, whatever. So about 26%, right? You with me so far? So for this little experiment that they did, where they got 157 yellow peas, 446 green peas, and they were crossbreeding the things, turned out they ended up getting about 26% yellow peas. But what they want is they want a 95% confidence interval. Now, what is that? We just began to talk about that last time. They want to be sure. This is all about sureness, right? Statistics is all about being sure, because luck could always get in there. Something sort of random could happen. You could just happen to get a lucky amount of yellow or green or whatever. So you want to rule out luck. You want to say, how sure are we? So we want to become 95% confident. That's exactly what it means, just what it sounds like it means. We want to be 95% sure about the true percentage. Now, is it truly 26%? That's what we got. When we did the yellow and green peas, we got about 26% yellow. But maybe we were just getting lucky and it's only 20% yellow. Or unlucky and it's 30% yellow. Or I don't know if getting yellow is more lucky or less lucky. Whatever. Maybe we just got some random luck in there. Yes, in our little experiment, we got 26% yellow. But is that really what the truth is? When you mix these yellow and green peas, does it really, what's the truth? You know what I mean? We're always interested in going after the truth. Just like election, right? Remember, that's the great analogy where we wonder, how many people are going to vote for candidate A, and then they poll and they poll and they poll, and then the real day comes and we see the truth. Well, so there's some truth, some scientific principle about how the yellow and the green peas produce their offspring. And we're wondering, we did a little experiment on 603 peas, and we got about 26%. We'd like to be 95% sure what the real percentage is. How do you do it? Well, it's on the calculator. So let's take out our calculators, and it's under tests. You hit go to stat, hit the stat button, and then go over to tests a couple of times to tests. And then hit enter, and then go down the tests, all the way down to the one that says, it's on A on my calculator. It says 1 proportion Z. It's way down the list. 1 proportion Z interval. It's on option A. Mine go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A. So that's where I found mine. Select the 1 proportion Z interval. That's a confidence interval. And then it'll ask you for a couple of things. It'll say, give me the n value. No, sorry, the x, huh? Give me the x value. Give me the n value. So what is the x? What do they want? Well, that would be the number that actually came out yellow. So for us, that's the 157. So it's the number of whatever you're measuring. So in this case, yellow peas, 157. And what's n in every statistics formula, basically, always? Total number. It'll never stop being that. It's always the total number. So what's that? 603. So you're with me? The X is 1. Now, how do I know? You might wonder, a good question, I think a good question, would be like, well, how do you know, Mr. Aaron, if it's the yellow? What do you put there on the X? Do you put the yellow? Do you put the green? Well, it's just because of what they're asking me to do. They want me to find the true percentage of yellow. So I put the number. X is always what you're finding, in this case, yellow. So I put the 157. If they asked me to find the true percentage of green, then I would make X be the green number, you know? And then what do we do after that? Oh, and then there's the confidence level. So we're doing a 95%. So just type in point, confidence, C level, 0.95, and then just hit enter and calculate that thing. 157, 603.95. And I'm getting the following answer. It's telling me it's going parenthesis, what is that, 225? 225, I don't know how many decimal places it want it run. 3 decimal places, okay. 3 places, 0.225.295. Y'all getting that okay on your calculator? 0.225 to 0.295? How's that going?
You're at 95%.
Yeah, we're not now. Yeah, we're 95% sure. Remember, what we're going after is the truth. Just like in an election, right? If they were to form a confidence interval, and they might say, we are 95% sure that between 41% and 48% of the population is going to vote for candidate A. That'd be the kind of thing we're doing. And then on election day, the real truth comes out, and we see whether the truth was in their interval. Does that make sense? We're trying to get bounds, interval, on the true percentage that are yellow. So we are 95% sure that really, the truth about what the yellow-green mixed thing will do in the long run. You know what I mean? There's always random results, intermittent, but we're 95% sure that the true percentage of yellow peas is going to be between 0.225 and 0.295. Is that confusing? Because I know you might think, what do you mean? We already did it. It's, I would wonder, I would assume many of you would be thinking, what are you talking about, Mr. Aaron? It's 26%. What do you mean we're 95%? Well, remember, the 26% is what we call p hat. It might help to actually give that a name and a label. P hat means that's a sample. In other words, that's not the truth. That's just what happened in our little experiment. Do you know what I mean? Like how about this? I might flip a coin. And I might flip it 100 times and get 60 heads. And then I would say, okay, so this coin flips heads 60% of the time, always. Well, now, that's just what happened when I did it 100 times, right? There's a difference between what happens in my sample and what the overall truth is. Meaning, if the life of that coin through its next 100 years of being flipped, we know it's 50% chance of heads, huh? That's the real truth. Does that make sense? So you want to distinguish in your mind the real truth from the sample results.
So you would put 60, 100, and 0.95 when you punch it in if you're doing flip coins, and then
yeah,
and it'll give you the in between those two dimes.
Yeah, it would give you a confidence. That's right. Exactly. Is that making sense on that? You get the idea, because I want to make sure you catch the big idea of a confidence interval. You're trying to get to the truth. You don't know what the truth is, right? You did a little sample, you did a little experiment, and this is, we're really getting into the heartbeat of statistics here. This is where stats is really used. This is the general thing stats does, is try to get, let's do something more important than yellow peas and green peas. What if there's a new treatment for cancer, right? And they're saying for a certain kind of cancer, and they're saying, we want to know what percentage, should we go with the new treatment A or the old treatment B? And they've only done the new treatment on 100 people, but for those people, 70% were cured, and the old treatment only cured 50%, so we're thinking the new one's better. But are we sure? Maybe those 100 people were just kind of more healthy by luck of the draw, How do you know? Well, that's the whole thing we're doing here. We're determining how much luck could possibly get in there and how much couldn't. We're trying to get to the truth. So we're saying we're 95% sure, confident, that the real percentage of yellow peas that if you just keep doing this thing forever, that what you'll get, the real percentage will be between 225, 22% and 29%, or 23 and 30, however you want to round it. Is that making sense on that? So they'll ask you questions about that truth. Let's go on and see. Okay, so it says, given that the percentage of offspring is not 25%, given that the percentage of offspring yellow peas, do the results contradict expectations? Right, so it says here, it was expected that 25% of the offsprings would be yellow. That's what they predicted. The scientific theory beforehand predicted that 25% of the peas would be yellow. We didn't get 25%, did we? What did we get? 26%. So do our results, but then we get this confidence interval. So if you're a scientist doing this experiment, does this contradict your theory or support your theory? And if so, why? Do you understand what it's saying? Support. First off, does it support or reject? Why does it support, even though it came out different than 25?
Because it's in between 225 and 295.
Yeah, because even though we got 26%, that's just what happened in the sample. We are 95% sure that the real percentage is between 225 and 295. Is 25% in that zone? Absolutely. You see, if this was some zone not including the 25%, then that would reject our theory, at least with 95% confidence. Do you see the deal? If we're thinking the real truth is that 25% yellow peas, well, that 25% is in our interval. That's included in our confidence. Does that make sense? That's not in disagreement with our results. So we agree with that. Does this contradict? No. The confidence interval 0.25, it includes it. That's in our interval, right? Our interval went from basically 2.3 to 3.0, didn't it? So 25's in there. So the true percentage could easily be 25%. That makes sense? So the idea of a confidence interval is you use sample results to give you some confidence about what the truth may be. Okay, so basically they're saying, hey, how often do you not get an accurate order from restaurant A? That ever happened to you? You go through the drive-thru, you get your food, you're down the road, you open the bag, and there's something wrong, right? I always think they should, I always appreciate those drive-thru people that say what's in the bag as they hand it out. That became my obsession. I worked at Arby's for 5 years, and a long time ago, and when I was going through my college years. But yeah, when I did drive-thru for a while, I would tell people, boom, boom, boom in that bag, boom, boom, boom in that bag. I think, just tell them. Just tell me what's in the bag. It's double-checking, communicating. I'm probably just obsessive, but I always think, tell me what's in the bag. That way you know it, I know it, we're all good. Anyway, so we're saying what percentage is not accurate? So, all right, so can we form a 95% confidence interval on what percentage are actually not accurate?
0.190 to 0.297.
Yeah, so let's do our thing. So we have the X and the N and and we're doing a confidence level. That's 0.95. So what's the X?
61.
Yeah, 61 are not accurate. What's the N? Remember what N is?
Total.
Total. Yeah, N. So you got to add those up. What's that? 311. So N's always the total number, right? So put that in. Let's see what you get. I'm getting, here's what I got. 0.152, comma 0.240. All right, so we're 90, so this restaurant, we're 95% confident that truly they make between 15% and 24% inaccurate orders. We're 95% sure that the real, not just our little sample of 311 times, but just overall and what this restaurant does in general, that this percentage of the time they are inaccurate. Is that making sense what the confidence interval is? And what do they want to ask me about it? So you put those two answers here and here. Just type those in. And they want you to round to 3 places. So I would just put those in. What were they? 0.152. What was it? 0.240? Okay.
Yeah.
0.240. And then they say, okay, so, and then what's part B? Compare the results from restaurant B. Here's restaurant B. They're inaccurate, not accurate, between 0.181 and 0.259. Okay. What do you conclude? What's their question? Compare the results. What do you conclude? Oh, no conclusion? Maybe because not enough information? The lower confidence limit of the interval for restaurant B is higher than the lower confidence limit for the interval restaurant A, and the upper of B is also higher than the upper for A. That's true. Therefore, restaurant B has significantly higher percentage orders that are not accurate. We don't know that, huh? Right? Now, C is right, isn't it? Since the two confidence intervals overlap, neither restaurant appears to have a significantly different percentage. Does that make sense? Because, right, they overlap. So restaurant B, let me write down restaurant B here, is 0.181 to 0.259. So we're 95% sure that restaurant B, between 18 and 26% of their orders are inaccurate. So it could be 18% or 19 or 20 or 21, 22, 23, 24, 25, 26. We don't know. We're just 95% sure that the real percentage of inaccurate orders that restaurant B cranks out is somewhere between 18 and 26. Restaurant A is between 15 and 24. There's a bunch of overlap. We don't know which one's really better or worse from this data. We would need more data. Is that making sense? Am I making any sense at all? Is that good? Because there's a bunch of overlap, right? I mean, A could be anywhere in this range. So A could be way up at 0.24. That could be the true percentage. We're 95% it's somewhere in there. We don't know exactly where. A could be like 23%. And B could be more like the bottom of his range, like only 19%. And B could be doing better. Less inaccurate orders. Or vice versa. There's just a bunch of overlap. So when their confidence intervals overlap, you don't know who's really the better one. We don't know who's higher or who's lower. Because there's overlap. Right? Is that good? All right. So, science fair. Emily conducting experiment. There's these professional touch therapists that claim they can, read your mind, sense your energy field, I guess. So basically, here's how Emily tests them. She flips a coin and picks a hand and has them pick a hand. If you read all these words. So basically, 298 trials, they were correct 139 times. So let me write those numbers down for you. 298 trials. The therapists were correct 139 times. So Emily just flipped a coin, and then she had them, pick which hand it was, and they got it right 139 times. So the question for us is, what they're going to ask first? Well, they're going to go through several questions. First off, given that Emily used a coin, what proportion correct would she expect if the touch therapist made random guesses? If they're just randomly guessing, and they don't really sense an energy field at all, then what percentage would we expect? 50%, right? 0.5. They would just get it right about half the time if they're just guessing. And Emily's just flipping the coin, right? Okay, now, using her sample results, what was their success rate? So part A, random, correct, 0.5. B, what was the sample results correct? So they were correct 139 times out of what? Yeah, it's 298, huh? Yeah, we don't need to add anything. They're giving us that. So just divide that, whatever that is.
0.4664.
0.4. Yeah. So they were right, 4664. I don't know how many places they want you to round. And then using Emily's sample results, constructed 95%, because maybe they just got lucky or unlucky or whatever. Maybe there is a truth there. Maybe they really can sense an energy field. Let's let statistical data lead us to the truth. Let's form in, was it 95%? Is that what they want? 95% confidence interval about what the true correct number is. So 95% confidence interval. So we have X in confidence level is 0.95. What's our X?
X is 139.
139. What N is just 298, right? So we just do it again. I'm getting 0.4098. I guess they want me to round to 3 places. Well, I'll write it down first. 0.4098, 0.523, 31. If you want me to round to 3 places, that'd be what? 4. How will 4098 round? 410, yeah. 410. 523. All right, so we're 95% confident that really, based on these sample data, really the therapist can sense your energy field. The truth is somewhere in that zone. So is there reason to believe? Well, here let's see what they ask. How do they ask it? What do the results suggest about the ability of the therapist to sense energy fields? Let's try to read through it. Since the lowered confidence limit is below 0.5, there does not appear to be sufficient evidence that they can sense your energy field. Yeah, that sounds good to me, but I'd be nervous to grab A. What's the next one? Since confidence level is not entirely above 0.5, there does not appear to be sufficient evidence. Can select by, I like that one too. Yeah, B's looking better to me. Let's keep reading on. Since the upper is above, no, that's not enough. Since the confidence interval is not entirely below, to be evidence that test therapists can select, but no. Yeah, it is B. It is B. What's wrong with A? But basically, what would you need for your confidence interval to believe? Think about what you would need to believe there is strong evidence that the therapist can really sense your energy field. You would need to have the interval all be above 0.5, be above luck, right? If it was like 0.6 to 0.8 or whatever, we'd be a believer, right? We'd say if there was a 95% chance that the therapist could really sense they were picking the right hand between 60% and 80% of the time, then they're doing something beyond luck. Because luck should only be 0.5. 0.5, we're 95% sure that there's something more than luck happening. But we didn't get that. 0.5 was in our interval. Am I making any sense? Are you getting the meanings of what these things say? To have significant results, you've got to be statistically have strong evidence, 95%, that there's something more than luck happening. And we're not. That would be like if you'd gotten some interval that was all above 0.5, then you would have that evidence, right? That if the interval came out like 0.6 to 0.8, and we're 95% sure, we would say we're 95% sure that they're above 0.5. So there's something more than luck happening, but that didn't happen. Our interval includes 0.5. So it's just luck. At least there's no strong evidence otherwise, anyway. Does that make sense on that? Questions? Does this seem doable? We want to estimate the true percentage of people who graduate with their bachelor's degree in 4 years or less. Does anybody do that? That's hard to do. It took me like 6.5 or 7 or something. Anyway, 4 years or less. So find the sample size needed to estimate. So suppose they're getting ready to do a study. They're like, hey, we want to do this study. We want to, start asking people at Fresno State or wherever, what percentage of them got their degree in 4 years or less. Now the question is, how accurate do you want the study to be? They want to have it right within 0.04 margin. Does that make sense? In other words, that margin of error means, like if it comes out to be like 20%, give or take, add or subtract 0.04. Does that make sense? They want to know, is it 0.20%, add 0.04, subtract 0.04. They want to have it, that's the, from the middle, above and below, that's the width of the margin from the middle, above and below that they want. That's how precise they want to know it. Am I making any sense what that says? Because when you do a study, you don't want to say, well, we're 95% confident that somewhere between 1% and 99% of all people graduate in 4 years. Well, you're saying nothing, right? You realize that would be lame. So let me give you the big idea. The idea is you want a somewhat narrow margin, or you're not saying anything. I could say that right now. I'm very sure that somewhere between 1% and 99% of all people graduate in under 4 years, because I'm not saying anything. Of course it's between 1% and 99%. But the question is, can I say something more narrow? The more precise your statement, the harder it is to say that, right? The stronger evidence you need to say a more precise statement. So they're saying we want to say something with only an error margin of 0.04. We want to make a very accurate statement. So if you want that kind of accuracy, that means you're going to have to talk to a lot of people. Because the more people you talk to, the stronger your evidence gets. You know what I mean? Think about the cancer treatment thing. If we only said, hey, 70% of the people treated with this new treatment got better, but we only gave it to 10 people. Well, that's not very strong evidence, is it? But what about if we gave it to 100 people and 70% got better? Or 1,000 people and 70, or 10,000, or 1,000,000 people? The more the number of people from which your data comes, the stronger you believe the results, right? That's what we're determining here. If you want to be sure, you got to ask more people. That strengthens data's believability, right? So you write these down, and this is what we're doing right now, is this stuff right here on 12, 13, 14, 15. So the question, if you're going to set out to do a study, the first thing you got to determine is how many people do I need to talk to if I want to do this study? What do I want to do? I want to make a statement that has no more error than 0.04, a very precise statement. And I want to be 99% confident that I've got the true value within 0.04 error. That's going to require a lot of people. So let me write those facts down for you. We want a 99% confident interval, error margin of only 0.04. And part A says, assume that nothing is known about the percentage to be estimated. So part A says, you know nothing about p hat. You have no idea. Like, I have no idea what percentage graduate in 4 years or less. I'm just clueless. So how many people do I need to talk to? Well, that's the information I'm giving you right here. In fact, let me write it so it'll be on the YouTube. Also, I should do that, huh? I almost forgot. So here we go. So on problems 12, 13, 14, and 15, what you're trying to find, all these problems, you're trying to find n. That's your goal. Find the number of people you need to sample. Find out how big your sample size needs to be. How do you do it? Case 1, when no p hat knowledge, when you know nothing about p hat, what do you do in that case? The number you need to sample is z squared 0.25 over e squared. Whoop. Oh, I did those backwards. I'm sorry. Those are wrong. They're close. You just got to swap one part. Here. All right, so z squared 0.25 over e squared. When p hat known, when you do know p hat, first off, q hat is 1 minus p hat, and then the number will be z squared times p hat times q hat over e squared. All right, and then and what is E? Well, I'll write it over here on the side. E equals your air margin. And P hat is your sample percentage. Sample percentage. And then the table. I gave you that table to try to make life a little easier. So the confidence level. So if you want 95%, what would I do? Oh, 90, 95. Okay, 90, 95. So 90, 95, and 99. Here is the Z value you need. 1.645. So you're going to want to put these on your 3x5 card for the next exam. We're already talking about the next exam. 2.576. So there we go. So that's correct on the board now. If you took a picture, take another one, because now it's right. If you wrote it down, fix it. Sorry. All right. So that'll be on the YouTube. It's on the board. All right. Let's go to it. Oh, it's right there. It's all right there. It's correct up there. Oh, you want to light it? That better? Wow, I feel like it's a photo. I feel like a celebrity. Should I be in the picture? With all the cameras. I've always wanted to be, you know? That's right. All right, so let's finish up this question. Time is running. So let's do at least one of these. So, all right, so how do we go through this calculation? Basically, N is going to equal Z squared times 0.25 over E squared. Oh, important word. I forgot. I'm forgetting a lot tonight. Which I think is funny. You might not think so funny. Round up. Round up. Everything goes up. Even a 0.1 goes up. That's what I mean. So we round these answers up. Why? Because more people is always improved accuracy. If you're supposed to, right, we'll see when we get an answer. All right. So round up. More is always better when you're talking about your sample size. So let's go to it. So let's plug in our stuff and crank out our answer here. What's our Z value? 99% confidence interval? 2.576. So 2.576 squared times 0.25 over E squared. What's E? 0.04. Oh, yeah, they gave it to me, huh? Boy, right there. Thank you. 0.04 squared. Can you hit the buttons on your calculator? That's not easy to do. You know where your square button is and all that stuff? I'm getting 1036.84. And what do I do with that number? Round up. Even if that was not 0.84, even if that was like 0.04, I would round it up because we're saying talking to more people improves accuracy. In other words, this answer means that you need to talk to 1036.8 people. You can't talk to 0.8 people, so you talk to more, and that improves your accuracy. That's how many people you would need to survey to get the kind of accuracy they're desiring to get.
Wait,
how are we doing?
Do we do divide 04 and then square and then answer? Or do you do 04 answer and then square?
You just put the square right on the 04. All right, well, it looks like we are out of time.